All right, it's about 1:15, so we're going to get started here. So thank you, everyone, for coming. First of all, I am Ryan, and I am the tech lead of the user data team at Twilio. And I'm going to talk about 3 topics today. So the first topic is going to be about the history and evolution of our database infrastructure at Twilio, from where we started with a few single MySQL instances to where we are today with a few sharded MySQL clusters, as well as some of the managed databases that we've started to adopt, such as DynamoDB and Redshift. Second topic will cover some examples of how we have started to adopt some managed database services into our infrastructure and into our applications, and 2 concrete examples with DynamoDB and Redshift. And then finally, I will wrap up with how the adoption of managed databases has influenced and affected us as an engineering organization and as a culture. So first of all, for those of you who are not familiar with Twilio, we are a communications as a service platform, and we provide an API that allows application developers to embed voice over IP and messaging into their applications. So a very simple example of how it works is when you sign up with Twilio, you purchase a phone number. And with that phone number, you configure an HTTP URL. And when a call is made to that phone number from another phone or some other client device, Twilio receives that call, and we turn that into an HTTP request that we send to the URL that's configured on that number. We take the response from your application server and process the instructions that it provides. So for example, your application might return XML that plays a message and then forwards that phone call to another number. So what is the user data team at Twilio? So we have 3 primary responsibilities. So the first is that we scale and manage our backend database infrastructure. So these are all the databases that store all of our customers' historical call and messaging data, as well as some other data at rest. On top of that infrastructure, we build customer-facing data APIs. So if you make a request to the Twilio API to get your call or message history, our backend service is actually what fulfills that request. And then finally, we manage all of the data policies and the security around that data at rest. So a little bit about the history of database infrastructure at Twilio. So for those of you who have developed a communications application before, know that communications are inherently stateful. So for example, here, a call can go from queued to ringing to in progress to completed, and a message can go from queued to sending to sent to delivered. And the pipeline through which these states are transitioned and stored forms the backbone of Twilio, on top of which the services within Twilio operate on. So in the beginning, things were very, very simple. Back in 2008, we were still a startup, and our deployment and our databases our deployment with our databases was very simple. All data was placed in the same database and the same database table, regardless of where a call or message was in its lifecycle. And so we call this the monolithic database model. So in this example, you have an API service, a web service, and a billing service, all talking directly to MySQL cluster, or a MySQL master. And you have the call and messaging service, which actually does the transitioning of states for calls and messages and interfacing with carriers, also talking directly to that MySQL master. And so this works fine when you are small, when you do not have too much traffic, and when you're still growing, it works pretty well. But once you start to scale, once your growth starts to accelerate, problems start to manifest. So these are a few of those problems. So you have many consumers of data, all with different use cases and different performance characteristics. So you might have in-flight systems that are handling the state transitions for calls and messages, and those require high write throughput. And then you also have the API or the website, which mostly reads data, and that needs to be optimized for read throughput. And what ends up happening is, because all of that data is stored in the same physical location, you can't optimize for either case. You also have clients that are implemented in many different languages and platforms, and each of them have their own pooling and connection semantics. So when the database goes down or the database fails, the behavior of the service in degraded mode becomes incredibly difficult to reason about. And last but certainly not least, horizontal scaling and orchestration is complicated because all of the clients need to be updated to account for the changes that are made to the data store. So a lot of this can be solved by moving to a service-oriented architecture or a microservice architecture. So the way that I define a service-oriented architecture is it's an architecture in which required system behavior is decomposed into discrete units of functionality implemented as individual services for applications to compose and consume. So the way you might think of the previous model evolving into a service-oriented architecture, so in the previous model, all the clients were talking directly to a database and essentially communicating through the database, using the database as a communication mechanism. And so the way that this evolves and has evolved in our infrastructure is we now put services in front of the databases. And we also store the in-flight data separate from the post-flight data so that we can optimize the use cases for that data separately. And so now all of the clients of that data talk to the services rather than directly to the databases. And this allows for changing the underlying storage technology or changing how the data is stored without having to affect all of the clients. So for example, if we wanted to move the post-flight database to DynamoDB instead of MySQL, then the only service that needs to be updated so long as it satisfies the same contract is the post-flight service. So SOA is great, but it doesn't solve everything. No matter how many services you put in front of MySQL, it is still a single point of failure. And it still does not scale horizontally by default. So you need to solve the scaling problems in the application layer. So I'm going to talk a little bit about how we shard MySQL at Twilio and how we pulled that off. So implementing sharding is actually really easy. There's really 4 steps. There's choosing the partitioning scheme, implementing the routing logic, sending application queries through that router, and then deploying. And then you have a sharded infrastructure. And the way that works today is we subdivide our key space for all of our records into ranges. And we have a router that routes queries for each of those ranges to each of the individual shards. So in this case, you have IDs, queries that reference IDs 0 through 3 go through to shard 0, 3 through 6 to shard 1, and 6 through 9 to shard 2. And it's pretty simple. The hard part is rolling it out with 0 downtime. So if you think back to landlines, when you picked up the phone, what did you hear? You hear a dial tone. And if you did not hear a dial tone, either you did not pay your phone bill or something was seriously wrong. And so the way that we think about our API at Twilio is it is the new dial tone. And if you are not able to communicate with our API, it is just as bad. And we promise that our customers can depend on our infrastructure and our platform for their applications to communicate with the world. And so we provide a 24/7 always-on service. And for us, there really is no maintenance window. So how do we pull this off? So the first thing is we have an existing shard, shard 1. And at this point, all of the application queries are going to that first shard for the full key space. Then we bring up a new shard, shard 2. And we bring it up slaving off of the existing shard. And the reason that we bring it off slaving off of the existing shard is there was a point at which we will start writing to that new shard for a subset of the key space. And we want to make sure that at that point, that shard has all of the data that it needs to for that key space. So there's another problem in that we use auto-incrementing columns for our auto IDs. And the problem is while we have shard 2 slaving off of shard 1, and then we start writing to shard 2, the generation of those IDs is local to a given master. And so if you start writing to both shards at the same time, there's a potential for both masters to generate the same ID, and there will be a conflict, and replication will fail, and you'll need to start over. So we use a handy little trick that MySQL allows you to do, which is you can configure the masters to generate different types of IDs. So what we do is we configure the first master to generate only odd IDs, the second master to generate only even IDs, and then we can start writing to the new master without fear of collisions. And then we cut the slaving link, and then we have a brand new shard that is consistent with the data. So this was really great when we pulled it off. And it was a big win for us because we could continue to scale. We can continue to accept new customers, continue to take new traffic. But with every new solution, there are always new problems. So the biggest problem for us was the operational overhead and the operational burden that came with managing a growing number of shards and running the actual operations to execute the sharding. So after the first round of sharding, 6 months passed, and we sharded again, and it was fine. We went through the same design, same steps, and pulled that off. And then our growth continued to accelerate, and then 3 months later, we sharded again. And then we started to feel the pain. And as our growth continued to accelerate, the time between when we would need to shard would decrease to the point where all we're doing is sharding operations and managing new database clusters. And so an important point to make here is my team is composed primarily of application developers. These are full-stack engineers who are not database experts. And so we're putting all of these application developers on these database operations, and at the cost of not actually developing new features and adding value to our platform. So rewinding back to 2008, when Twilio first launched, there really wasn't much in the realm of managed databases, or at least there weren't managed databases that we could trust enough to build a real-time communications platform on top of. And so in the beginning, that burden of managing our own databases was non-negotiable. Fast forward to 2014, and things have changed quite a bit. So we have a variety of managed databases outside of Amazon and within Amazon. And within Amazon, we have RDS, DynamoDB, SimpleDB, and Redshift, and new databases, as you learned of this morning. So another big problem is that because we have application developers managing these databases and designing these databases, cost is never optimized. We focus first on scaling, and then once we get things working, we shift our focus back to building applications and features. And so what ends up happening is, over time, that adds up. So this is actual data from our team at Twilio. This is the cost of infrastructure, and you can see that databases are a vast majority of the cost, 78% compared to 22% for everything else, which is a lot. So as growth continues to accelerate and the operations continue to increase, how do we keep up? And so we really need to take a step back and change our approach. And there's really two options. We can either change our hiring practices and bring in specialists, bring in teams of database experts, or we can remove the operational burden and the context switching. And this sort of begs to me, this begs a philosophical question around what does Twilio do? What does our company do? Why do we exist? What value do we add to the world? And while we are successful in scaling databases and operating them and growing them, we are a communications platform. We're not a database platform. Data is an essential part of our platform, but the databases themselves are an implementation detail of how we execute our service. And so really what this boils down to is focusing on what we do well, which is communications, not databases. So with that in mind, over the last year or two, for new products and existing products, we started to move a lot of our infrastructure over to managed databases instead of the unmanaged MySQL that we were running previously. And I don't have time to go over all of them, but I'm going to go over two examples. One is a post-flight events API. And just to clarify some terminology here, through the data pipeline within Twilio, there's a point at which data becomes at rest, and we classify that as post-flight. And so we have a group of services that manage that data and operate on that data that is at rest. And then once it becomes post-flight, we need to get that data into our warehouse so that we can run business intelligence on that data. And so when we were building the post-flight events API, we evaluated some managed database stores, and the one that we chose was DynamoDB. And so I'm going to talk a little bit about why we chose DynamoDB and how we modeled our data with DynamoDB. So one of the things I really love about Dynamo is it allows you to think in terms of throughput. So with EC2, we bring up machines. And we bring up machines with a specific amount of RAM and a specific amount of disk, a specific amount of bandwidth. And this is a lot better than where we were with managing and provisioning our own hardware, but it is still not as nice of an abstraction as an application developer would like. DynamoDB takes us a step further and allows you to provision in terms of pure throughput, so pure reads per second and writes per second. And that makes the reasoning about how much resources and what resources you need much simpler. And to me, this is really the future of resource provisioning. Operations, we focused a lot on the pain of operations. So DynamoDB and all managed databases have a dedicated team that is working behind the scenes, unbeknownst to you, scaling that backend data store, handling all the failure scenarios. And so that burden is completely taken away from us. And so now we can focus on building the actual applications on top of that. And I mentioned cost. So again, we don't optimize for cost because we're application developers. The cost of DynamoDB compared to our MySQL infrastructure is, it's almost comical. It's 18% of our MySQL costs on our team. And this is more for illustration purposes. We don't have everything replaced with DynamoDB today because it doesn't fulfill every use case. But let's say that we did, then our database cost becomes a minority of our infrastructure cost, which is a pretty big change. So moving from a relational model, which a lot of our application developers are familiar with, to the model that DynamoDB provides, requires a little bit of remapping of how you think about things. So I'm going to go over one of the endpoints with the service, the post-flight event service that I talked about. So the post-flight event service allows you to look up and retrieve events that were generated within our system in certain, under certain conditions for an account. And so in this example, we have an endpoint where you can retrieve the events for an account. And this actually maps pretty nicely to a SQL query. If we were storing these events in a single table, it would just be select star from events, order by date, and you're done. And then we also support some filters, which we expose as query string parameters in the service. And so, for example, we allow pulling of events that were generated by a given IP address in the system. And so if you wanted to pull all of the events generated by a given IP address, that also translates pretty simply and easily to SQL. And then we also allow you to filter by date. And again, that maps pretty easily and simply. So how do we model this with DynamoDB? So first of all, if you're not familiar with DynamoDB, the way that you structure your tables is you have a hash key. And that hash key determines under what value or what key or what field all data is scoped. So in our example, we want all the data, when we access data, to be pulled back for a given account, and so we use the account ID as the hash key. And then you have an optional range key, which allows you to define the sorting order for your records when you pull them back. And so implementing the first endpoint without any filters is pretty straightforward. We have account ID of 2 and scan index forward equals false, which just tells Dynamo to return those results in reverse order. And you see that there's this funny IP address date field here. I will go over that in a few slides. So how do we support filtering by IP address? So we store the IP address and date field together. And again, I'll go over that in the next slide. But to pull all the records that were generated by an IP address, we do a prefix match on that field. And so that field always has the IP address first, a delimiter, and then the date. And then we use begins with, which is Dynamo's way of doing a prefix match on that, and specify that IP address. And this implements the semantics that we want. So how do we support filtering by multiple fields or multiple values? So the way that indexes work in DynamoDB is you only index one field. You cannot index multiple fields like you can with MySQL or other relational databases. And so the way that we do this, and this is why those fields are combined, is we store the IP address in addition to the date in a single field, and then we index that one field. So if we want to filter on both of those values, then we combine the filters into one, and then we specify that to Dynamo. And in this case, we want to pull all records that were less than a given date, so we use the less than comparison. So some things that you need to keep in mind when working with DynamoDB. The first is that you need to handle exceeded throughput failures. So this actually isn't much different than if you were writing against a managed databases. You still need to handle the case where you exhaust that database's resources and that database fails. So you need to do the same thing with Dynamo, but I feel like there's a tendency, because Dynamo kind of scales magically for you behind the scenes, that this sort of gets left to the wayside. So if you provision a certain amount of throughput for your DynamoDB table and you exceed that throughput, that manifests as a runtime error. The way that we deal with that at Twilio is we use SQS between our writers and DynamoDB, and then we process those events asynchronously. So in this example, we have an API node, a web node, and a billing node, and all of those generate events. They send them to SQS, and then we have an events processor that asynchronously processes those events from SQS. And if the insert fails for whatever reason, let's say that you exceed the provision throughput or there's some other failure, to handle that, we just don't delete from that event from SQS. And then the next time the processor runs, that event will come back and we will reattempt the insert. And so we handle that gracefully there. Another thing you need to keep in mind is there is a maximum of 5 global and local indexes. So if you need more filters or you need to index more columns, you can either manage them yourself as a separate table, which I don't recommend because then you need to handle partial mutation failures in your application layer, or you might evaluate some of the other managed databases that Amazon provides. There's also a local secondary index size limit. So local secondary indexes allow for immediate consistency. So if your application requires that all data read needs to be up to date, you can use local secondary indexes to guarantee that. But to provide that guarantee, Amazon limits the size of that to 10 gigabytes. So you just need to be aware of how big your data set can be. So talked about how we've used DynamoDB for our post-flight system. Once data goes beyond our post-flight system, it needs to get into the warehouse somehow. So I'm going to talk a little bit about how that works and how we've moved from using MySQL as a warehouse to Redshift. So first of all, a brief history. In 2008 to 2011, all of our business intelligence queries ran on replicas of our MySQL clusters that were serving the same public traffic for our API. And this worked sometimes, but the way in which our business intelligence queries needed to access data was sort of at odds with the schema. So there were some queries that took either a really long time or were impossible because of the schema. In 2011 to 2013, we changed that and we pushed data from MySQL to S3. And that allowed us to query it with Pig and Elastic MapReduce, which gave us the ability to aggregate that data and access it in the way that we needed. But the latency was not where we wanted it to be. So depending on the size of the data set and the complexity of the query, that query could take on the order of hours to days. And then in 2013, we moved that to Redshift. And Redshift is magic. It is really amazing. It literally cut the time that these reports took from hours to seconds and allowed us to answer very critical financial questions that we use the warehouse for in near real time. So back when we were loading that data into S3, because we're loading that data directly from our MySQL clusters and putting it in S3, when we move from MySQL to another database technology like Dynamo or RDS or other technologies that we've been looking at, we would need to recreate the logic that loads from that database into S3. And so that wasn't really a tenable solution for us. So we changed it a little bit. And so instead of the warehouse loaders pulling directly from the database, we now push the data from our post-flight services, which is the sink for all the data that is at rest, into our event bus, which we use Kafka for. And then we have an S3 loader that takes all of that data, batches it, and shoves it into S3. And we batch it because Redshift is optimized for batch loading data. It's not optimized for inserting individual records at a time. And then we have a warehouse loader that runs periodically and pulls that data from S3 and batch loads it into Redshift. And so now if we change the actual database for post-flight, because now we're pushing data instead of pulling it from the warehouse loader, that doesn't need to change. And so they are now decoupled. So to wrap up, I want to go back to the point about focus and focusing on what we're good at and how that relates to managed services and managed databases. So at Twilio, our focus is on creating an experience that unifies and simplifies communications. And by leveraging managed services and managed databases, that allows us to not be distracted by all of the operations and all of the work that needs to be done to maintain the systems that don't add value to our product directly. And so I see the focus as something that is reflected in our adoption of managed services. And so really what it boils down to is by understanding our focus and knowing what we do well and letting the experts and the people who are dedicated to the other problems do that work for us allows us to accelerate the delivery of value and innovation to our customers. And that's it. We have some time for questions. Yep.
Any caching technologies for your in-flight data?
The question was, do we use caching technologies for in-flight data? We do. So depending on the in-flight system, some of that data is kept in memory. And today we use, in some places, we use Memcache and Redis. In other places, we use Hazelcast, which is a JVM-based in-memory data grid. There is some data that we cannot cache just because we always need to make sure that it's up to date. And, but in other cases, we try to use the caching services that are available to us. And we're looking at Elasticache right now. It's not something that we've historically used, but it's something that we're planning to move to in the future.
You mentioned use cases that DynamoDB didn't support to your liking.
Sure. So I mean, any use cases that requires you to access data in a relational way. So if you have to access data that requires a lot of filters or to do aggregation on that data, Dynamo doesn't really fit that model. And sometimes it can fit it in very simple use cases like the one that I showed. But as that complexity grows, it starts working against you. So it doesn't fit everything, but for what it does fit, it's really good at.
How do you deal with transactions?
In Dynamo?
Well, in general, I feel like with things like Dynamo or Cassandra, transactions become more of an issue.
Yeah, so the question was, how do we deal with transactions? So that's a good question, and I think that kind of is one of the cases where Dynamo isn't as good as MySQL. So for systems that require some transactional guarantees, we still use MySQL because Dynamo just does not have that built in. I know there's a library that adds transaction support on top of Dynamo, but I don't have any experience with that.
So the scaling is still an issue with the transactions?
Yep.
From the previous talk, it sounded like you guys are in multiple regions. How do you deal with that on a database level?
So today we actually are still working on that. All of our databases are still in US East 1. As somebody mentioned, when we decide to move our databases to VPC, the way that we'll likely do that is we'll bring up replicas slaving off of the master in VPC, and then slowly move traffic over to that, and then we'll promote one of the slaves in that VPC region. We have explored, how we can do cross-region replication. Obviously, the latency is much greater cross-region, and so for some of our systems that are very high throughput, that can cause problems with slaves getting behind and the data just taking a lot longer to make it across the world. But I know that if you read the Amazon blog over the last few days, they just announced streaming change sets for DynamoDB with Kinesis. And so that's a really interesting use case with cross-region replication. Yep. Anything else?
What happens like in Kafka? Please elaborate a little bit on that.
Sure. So the question was, why did we choose Kafka for our event bus? So we operationalized Kafka about 2 years ago, and at that time it was the most mature pub subsystem, real-time pub subsystem that we had evaluated, and we're currently looking at whether Kinesis can fulfill that same purpose in our infrastructure, but we're still kind of early on in that. Sorry? How do you expire data in Dynamo? Do you mean how do you delete data?
Yes. Do you let data keep forever, or I saw you using a account ID. Do you use any timestamp?
So that's a good question as well. So the question was, how do we delete data in Dynamo, and do we keep it around forever? So our system is designed so that we don't keep data around forever. And right now, the way that we handle that is we do have timestamps for every record. And then whenever we need to apply the retention policies for data within Dynamo, we have a process that runs, and it's throttled for throughput. And so it will only consume a percentage of throughput, and then it'll go in and delete the data within Dynamo. Another interesting design I've seen before is if you can constrain the window of time by which you retain data, then you can basically partition your data with different tables. And with that design is really nice because once that time window rolls off, all you need to do is drop that table, and that doesn't consume any throughput.
When we talk about the culture, I'm curious as to how big your database team is compared to how large the rest of the development team is, and if you've been able to keep that relatively small compared with these new technologies.
Yeah, so the question was, how big is the database team, and how do we keep up with the growth of these databases, and how do we manage them? So my team is 5 people, and we're not the only database team, or we're not the only team that manages databases at Twilio. So the way that our organization is structured is we're very vertically aligned. So we have teams oriented around certain features within Twilio. So we have a team that handles all of the voice connectivity to carriers, and we have a team that is responsible for the actual platform that we build on top of. And so historically, all of those teams were responsible for operating their own databases. Our team has the largest databases in the company, and so we are the ones that have been solving these problems first. But it's still a sort of distributed problem within our organization. Did that answer your question?
So that post-flight event pipeline that you guys created,
Yep.
potentially that's something that you could replace with 2 Kinesis streams, one to Redshift and one to S3, if you wanted the events to land in both places in the event.
Yeah. And so one of the other important things to point out is within that pipeline, there is some business logic that is specific to Twilio. So for example, we might need to encrypt data along the way, or apply retention policies along the way, or check if we should even store the data along the way. But yeah, technically, if we wanted to, we could replace some of that pipeline with Kinesis to do the pub/sub. All right, anything else? All right, if you have any other questions, you can find me after the talk, or I will be downstairs as well. But thank you, everyone.